Welcome to KnowAtom.com. We are Group 1B. We will be talking about variance in Chebyshevs inequality. With me is Otto, Daniel, and Michael. My name is Jesse.
Thank you.
Hello, my name is Michael Lasky. I'm here to talk about variance. Now, you might ask, what is variance? Well, variance describes how spread apart the values of a random variable are. Thus, given an average, it would tell you how far apart your random variables are distributed from that average. Now, why do we want that? We need to know it because given an expected value, we want to know how accurate that expected value is. If it has a large variance, then the expected value cannot really be accurate. You probably won't get that expected value. If you have a very small variance, you would certainly get the expected value that you predicted. What does this help us do? Once again, it lets us know how accurate our calculated expected value is going to be. Now, before we get really involved with variance, you need to have some background topics of what a random variable is, what a sample space is, what an expected value is, of course, or a mean of a set. For more information on these things, you should go to KnowAtom.com for more information. Alright, the mathematical definition of variance, and once again, this is assuming that you know what an expected value is the e to the x squared, or the expected value of a random variable x squared minus the expected value of x squared. Once again, e to the x is expected value mean, x is random variable in a given sample space. To help remember, mean of square minus square of mean. It's a little fun thing you can say to yourself. Alright, now here's an example. Let's say you want to calculate the variance of a four-sided die. So first you want to add up all the determine your sample space, which you can have 1, 2, 3, or 4, because it's a four-sided die, so these are different numbers that you can roll. And since you have to do x squared, you do 1 squared plus 2 squared plus 3 squared plus 4 squared. And then the probability of each would be 1/4, so you multiply that by 1/4, and you would get 15/2, and that calculates to e to the x squared. Then you have 15 divided by 2 minus 10 to the 4th. Now 10 to the 4th comes from if you calculated e to the x and you didn't have the squares, so you just do 1/4 times 1 plus 2 plus 3 plus 4, and that would get you 9 10 to the 4th squared, and then your variance would be 5 to the 4th. So what that means is you're going to have an expected value on the four-sided die of 10/4, or 2.5, right? So you're going to expect to roll around 2.5. I mean, obviously a 3 or a 2. But it's going to be distributed with a 5 to the 4ths. So really your expected value is going to vary a lot, and you're not really going to always get 3 or 2. You're also going to get 1 or 4 because your variance goes either direction, and when you map it, it's going to spread out to 4 and 1. That's what it's really saying. Now, some final notes on variance is use variance in everyday life when trying to figure out how spread apart things are. Examples are when rolling 2 dice, sums 6 and 7 are more likely than sums like 12 and 1. Because to get a sum, well, 1, when rolling 2 dice, you can't get 1, so because the sums don't add together. But also, because to get a sum like 6, you would have to have, or a sum like 12, you would have to have only one possible combination of 6 plus 6. Well, a sum like 6 could be 2 plus 3, 4 plus 2, 5 plus 1, and both of those can occur twice because you can have 1, 5, 5, 1. So you have a lot more different combinations where you can get 6 and 7 than 12, and you can have no combinations where you get 1. And variance helps you know the likelihood of results far away from expected or most common values. And like I've been saying, it's really important when you derive your expected value to know exactly how often you're going to get the expected value, and variance gives you that added information. So you can have an expected value, like before with the tetrahedral die, where we said it was 2.5, but your variance was 5/4, which really meant you're not going to get 3 and 2 most of the time. You were actually going to get 1, 2, 3, 4 evenly distributed. And it was that added information of variance that really helped you tie it all together and give you that added insight. But that's it for variance, and now Daniel's going to talk about Chebyshevs inequality theorem. Thank you.
Hi, I'm Daniel Neese, and I'll be talking about Chebyshevs inequality. Let us define an event A such that the result of a random variable experiment lies at least r away from the expected value. A little manipulation of the mathematical definition of this condition allows us to get that the probability of A occurring is less than or equal to the variance divided by r squared. Of course, the question arises as to what this is useful for. In simpler terms, this gives us an upper boundary on how likely it is for a random variable to be at least a certain distance from the expected value. We will cover examples of how this can be used later. In order to understand what Chebyshevs inequality means, it's important to understand what the variance of a random variable is and all the details leading up to this. If you're not familiar with these, there are additional resources available on kanoatum.com, and you can visit to learn more. In order to prove Chebyshevs inequality, we begin by noting that the variance of an experiment X is equal to the sum of the probabilities of an outcome times the square of the distance from the expected value for that outcome. We can break this up with a partition, where here A and not A, where A is once again the probability of the results landing outside R. Where A is once again the event of the result falling at least R away from the expected value. While we lack the details necessary to get an exact value, we do know that the probability for A is less than or equal to the probability for both A or not A. We also know that the minimal distance from the expected value in A is R, otherwise it would fall under not A. So we can substitute this in as another less than or equal to. This simplifies down to r squared times the probability of A, and rearranging this gives us Chebyshevs inequality. In order to help you understand this better, let's go over a simple example. Take a hypothetical exam with a mean of 84 and a standard deviation of 6. A nerd in class wonders what the probability is that they got 95 or better. Now, it's tempting to simply plug in the values to Chebyshevs inequality, but it's important to note that this would give us the probability that the nerd scored better than 95 or worse than 73. In order to correct for this, we divide our probability by 2, as we are only considering half the values. Our variance is 6, r is 95 minus 84, or 11, and so we find that the probability is a little under 11%. It's important to note that Chebyshevs inequality does not provide a very tight boundary, but only an absolute upper bound on the probability. In the real world, we can use this to get quick estimates on the maximum likelihood of random events, provided that the events are truly random. Let's try an example to show how precise Chebyshevs inequality allows us to be. Suppose 2 dice are rolled. We already know that the probability of getting a sum of 2 is 1 in 36, and the probability of getting a sum of 12 is also 1 in 36. The probability of getting either, then, is 1 in 18. In decimal, this is 0.055 repeating. We also know that the expected value of the sum is 7, and we are given the variance, 5.83. If we plug these values in for our variance in r, where r equals 12 minus 7, or 7 minus 2, which is 5, we get 5.83 over 5 squared. This is about 0.2332 in decimal. If we compare our results, this is more than 4 times larger than the value we computed by hand. It's clear that there are limitations on Chebyshevs inequality, a trade-off for its simplicity. Thank you all for listening, and please visit kanoatom.com for more great videos on discrete math topics.